Okay, guys, this is your Unit 4 Quiz 2 Study Guide help video. So I'll just go ahead and go through all the questions here. The first question is basically just about finding the derivative of a function, a piecewise function, from left and right of its boundary points, and then determining if the function itself is differentiable at those points. So the first thing we need to do is we need to find out, does the function actually connect at its boundary points? And to do that, we need to make sure that the limit from the left and the limit from the right of the function itself is in fact the same. So if I want to find the limit of w of x as x approaches -2 from the right, so first of all, if I'm approaching -2 from the right, then I'm approaching -2 from x values that are greater than -2, and therefore I'm using this piece. So we're going to be plugging in -2 into this piece here. And that gives me 1. Okay, now for the next question, we're approaching -2 from the left, which means we're coming at -2 from numbers that are less than -2. And so for that, we're going to be using this piece. Oops, plus 9. That's 4 minus 12, which is -8 plus 9, which is 1. So notice that the limit from the left and right of -2 are both 1. And therefore what that means is that these two pieces connect. They're not disjointed. Now we're going to do the same thing, but we're going to be finding whether or not the derivative is the same from the left and the right. That doesn't tell us if they connect, but instead it tells us if they connect at a smooth, differentiable curve. Okay, so let's go ahead and find the derivative now. I won't put equals, I'll just draw that. It's not equals. But the derivative would be 2x plus 6, and then 2x, and then 4, and then 2x minus 4. We don't know if the little equal signs are going to stay. They would stay if it's actually differentiable at those points. So I'm not going to put the equal signs yet. Maybe I'll throw them in later as time goes on. Just a sec. So no equal signs, but other than that, pretty much the same. All right, let's see if the limit from the from the right of -2 on our derivative, what that equals. So if I'm approaching -2 from the right, I'm looking for values that are greater than -2, and so I would be using that piece. So the slope from the right of -2 is -4. Let's see what the slope is from the left of -2. So if I'm approaching the -2 from the left, I'm approaching -2 from numbers that are less than -2. So that would be this piece on the top. So 2 times -2 is -4 plus 6 is 2. Now notice that the slope is not the same to the left and right of 2. So now that brings us to question E. Is the function differentiable at -2? And the answer is no. The reason it's not is because the slopes from the left and right are not the same. So how you would write that is you would say because the limit as we approach -2 from the right of w prime of x is not equal to the limit as we approach -2 from the left of w prime of x. Okay? All right, let's continue. Scrolling down. You know what? I'm going to do that a little bit different. All right, we're going to repeat the same exercise here, but now we're approaching 2 instead of -2. So we're going to do it for w of x and then w prime of x, and then we're going to determine is it differentiable or not. So let's go and do it. If I'm approaching 2 from the right, that means I'm coming at 2 from values greater than 2, which would be here. And so that's for 4x. So that would be 8. If I'm approaching 2 from the left, and I'm coming at values of 2 that are less than 2, which would be this piece here. And that gives me 1. Now I'm still going to answer the rest of the questions, but we can already tell right now that this is not a differentiable function at that point because this piece and this piece don't have the same left and right hand limits. And what that means is these two pieces don't connect, which means the function is not continuous. And a function cannot be differentiable if it's not continuous. But we're still going to answer the rest of the questions anyway here. So now I want to find what is the limit of w prime of x as I approach 2 from the right. I'm going to use this piece here, which would be 4. And as I approach 2 from the left for w prime, that would be this middle one here, I get 4. So I want you guys to notice that even though they have the same slope, the pieces aren't connecting at that point. So it's still not differentiable. So we're going to say, no, it's not differentiable, but the reason is different. This time the reason is not because the derivatives aren't the same from the left and right, but rather it's because the function itself is not the same from the left and the right. Okay? Okay, continuing on. All right, last one, we're going to see if this function is differentiable at 4 now. So if I'm approaching 4 from the right, that would be the bottom piece. So I'm going to be plugging in 4 here to the bottom part of the function. Which would be 16 minus 16 plus 16, which is 16. Then we do the same thing from the left of 4, which would be this third piece down. That would also be 16. So far, the pieces connect. Right? Now we're going to do the same thing with the derivative. So we're going to be approaching 4 from the right. Bottom piece of the derivative there would be 2 times 4 minus 4. That would be 8 take away 4 is 4. Repeating that process with approaching 4 from the left, we're going to be using the third piece down, which is 4. So notice that the left and right-handed limits of the original function are equal, so we know the pieces connect. And notice also that the left and right-handed limits of the derivative function are equal, which means that they connected a smooth curve, and therefore this is actually a differentiable function. So we're going to say yes, the function is differentiable at x equals 4, and the reason for that is because w of x is continuous at x equals 4, and the limit as x approaches 4 of w prime of x is what the derivative actually equals at that point. So back to the beginning here, we weren't sure if we would put the little equal signs, and none of them came out to be able to be differentiable except the 4. So this guy down here gets to keep his equal sign, no one else does. And there's your final derivative. There we go. All right, let's go ahead and do number 2 now. So we want to be finding the derivative of this absolute value function at -4 from the left and also from the right. Now, this is going to be one of our boundary points, and that's not immediately obvious, but just based on what we've been learning in class, you can be aware of it, that's the type of question we're going to have. So what we learned in class was that we want to change this into a piecewise function. And so the first thing that we do is we take our function and we set it equal to 0 and we solve for x. This piece here is going to give me -1, and this piece here is going to give me -4. So putting this on a number line, -4 goes on the left side, -1 goes on the right side. And now we need to test to see what happens on these 3 intervals that we have. Will the absolute value function change the sign of the output, or will it not? So let's go ahead and test some numbers. So I'm going to plug in -5 up here to this thing. So if I plug in -5, get a smaller pen tip here. So that's going to be 25 minus 5, which is 20, plus 4, which is 24. So 24, if you take the absolute value of that, it doesn't change the sign. So we're going to say for anything on this interval here where x is less than -4, there is no change in the sign. Okay? Now I'm going to pick a number between -4 and -1. So let's go ahead and plug in -2. All right, so that's going to be 4 take away 10, which is -6, plus 4, which is -2. And when you take the absolute value of -2, it will change the sign. So for the x values that are between -1 and 4, it will change the sign of the function. Finally, for anything greater than 1, -1, we're going to plug in, I'm going to choose 0 to plug in. If you plug in 0, these just go away and you're left with 4. And if you take the absolute value of 4, it doesn't change. So once again, no change happens there. All right. So that means we can rewrite this function now as a piecewise function. We know now that it's going to be x squared plus 5x plus 4 with no change in the signs for anything that is less than -4. We know that for anything between -1 and -4, the signs will be changing. And once again, for anything greater than -1, the signs will not be changing. Now we want to find the derivative. Derivative of the top is going to be 2x plus 5. The derivative of the middle is going to be -2x minus 5. And the bottom will be 2x plus 5. Now I'm not really too worried about my equal signs because I know that with an absolute value function, when you break it apart into a piecewise function, it's going to make a cusp anyway, so there's no point in putting equal signs if there's no derivative at these points. You could have equal signs up here, but it doesn't really matter because we're not going to use it for anything. All right, so now that we've got all that, we are ready to actually answer the question. So step 1 is to write a piecewise function. Step 2 is to find the derivative of that piecewise function. Step 3 is to go ahead and start answering your question. So now I want to find the limit of f prime of x as we approach -4 from the left. So here's -4, and to the left of -4 would be this one. So that means I'm going to be plugging in -4 into the top piece, which would be -3. If I'm approaching -4 from the right, that would be anything greater than -4. That's this piece. And so I'll use the middle piece for that. And negative 2 times negative 4 is 8, plus 5 is 13. Okay? I believe. Oh, I made a mistake. Sorry about that. It's not plus 5, it's minus 5. There we go. So 8 minus 5 is positive 3. So notice they're going to be the same, it's just they're opposites because that's where the cusp happens. So there you guys have it. That's for number 2. All right, here's another question we looked at. We have a piecewise function, and we want to find the values of a and b that make this thing differentiable. So the first thing we want to do is make sure that it's a continuous function. In other words, we want to make sure that the top function connects to the bottom function, and the only way that's going to happen is if the limit to the left of our boundary point is converging to the same point as we approach negative 1 from the right of our boundary point. So basically, we're just going to plug negative 1 into the top function for x, and we're going to plug negative 1 into the bottom of our function there. So if I plug in negative 1 on the top, I get that. And on the bottom, I get that. So that's negative a plus b is equal to 1 minus 3 minus 4, which is negative 6. All right, we're going to hold on to that. Now we're going to make sure that not only do they connect, but we want to make sure that they are connecting at a smooth curve. So we want to make sure it's differentiable. So what we need to do is we need to find the derivative of this function then. Let me bring up some more writing space here for a sec. All right. So the derivative of w, the derivative of ax is just going to be a. Derivative of b, that's a constant, so the b just goes away. I'm going to keep my equal sign because we're forcing this to be differentiable at negative 1. The derivative of the bottom, easy enough, is just 2x plus 3. So in order for this thing to be differentiable, that means that the slope from the left has to be the same as the slope from the right, and so it makes a nice smooth connection. So we're approaching negative 1 from the left with w prime of x, and we're also going to be approaching negative 1 from the right with the slope function. Which means basically I'm just going to be plugging in negative 1 at the top and the bottom and setting them equal. Now on the top there's nowhere to plug the negative 1 into. There's no x value, so that's just a. On the bottom, if I plug in negative 1, it looks like this, which means a is equal to negative 2 plus 3, which is 1. You may end up with a system of equations. In this case, you kind of really don't. This is pretty simple. You're just going to find out what a and b are now, you're just going to take your answer and plug it in. But don't forget, on your quiz, you may end up with a system of equation like we had in our notes where you have to do substitution or elimination. But in this case, it's pretty simple. I'm just going to plug 1 in for a, taking my answer from the continuous part. Plugging in 1 for the a there, I get negative 1 plus b equals negative 6. Adding 1 on both sides, I get b equals negative 5. And we're good. 2 answers. All right. All right, so number 4, the position of an object moving along the x-axis, that's important to pay attention to, is given by this function, where s is the distance from 0 on the x-axis in inches, and t is in seconds, and all answers should include units. So part A, where is the object located at t equals 4? All you do is you plug 4 into the function they gave you. So 4 cubed is 64 times 4, 240. I don't know. I can't do that in my head. 16, I think it's 256. All right, minus 30 or 16 times 8, 48 and 80 would be that 128. And then we're going to go ahead and subtract those, and I think it's 128. Yeah. Okay. So that's 128, and we want to say feet. Okay? All right, part B. What is the velocity? So to find the velocity, we need to find s prime of t. The derivative of this function over here is 12t squared minus 16t. And so we're going to go ahead and plug in the value they're asking us to plug in, which would be 4 again. All right. Yikes. I don't know. I can't do that. I need to calculate. All right. So 16 times 12, 192, minus 64, and it's 128 again, and this time it's feet per second is the unit that you would use for velocity. Part C, in which direction is the object moving? Since we are on the x-axis and it's a positive value, we are moving to the right. Part D, what is the acceleration? To answer that, we need to get our acceleration, which is the derivative of this function. I think I need some writing space here. Okay, so the acceleration function, oops, I don't want to invent a new letter there, so let me just put s double prime as the acceleration function. That would be 24t minus 16. So for part D, 24t minus 16. In this case, we're plugging in 4 again, I believe. Yep. And let's see what that is. 24 times 4 is 96. Minus 16 is 80. And the units for that would be feet per second squared as the units for acceleration. Part E. Is the object slowing down or speeding up? Since my acceleration is positive and so is my velocity, since the signs match, we would say it's speeding up. Is the object slowing down or speeding up when s of t equals 0? So that's actually a really big question. There's a lot going on there. So the first thing you have to do for part F is you have to figure out what time that happened at. So when does s of t equal 0? In other words, when does 4t cubed minus 8t squared equal 0? And we're going to go ahead and factor that to answer the question. There are 2 times when t equals 0. If I set this equal to 0 and solve, I get 0. And if I set this equal to 0 and solve, I get 2. So there are 2 points in time when the s function is at position 0. T equals 0 and t equals 2 seconds. Okay? So first of all, let's remember that. Now after we do that, if I want to know if it's speeding up or slowing down at those time values, then I would need to find both acceleration and speed for both of those times. So let's do that. So s prime of 0, if you were to plug 0 into this function over here, you're going to get 0. And if you were to plug 0 into s double prime, s double prime, I erased that. I believe it was 24t minus 16, right? So if I plug in 0 there, I get negative 16. Now, whenever your velocity is 0, which means you're not moving, but the acceleration is present, that means the object is moving up. So I would say this is speeding up. Now, if I were to look at s prime of 2, if I were to plug in 2 to this function over here, what would I get? Let's see. 2 squared is 4. 16 times 2, so we have 48 minus 32 is 12. So I end up with a positive 12 feet per second. Now if I wanted to find the acceleration at that point, 24 times 2 minus 16. 48 take away 16 would be 32 feet per second squared. They're both positive, and therefore, once again, that's also speeding up. So the question was, is the object slowing down or speeding up when s of t is 0? S of t equals 0 at 2 points in time, 0 and 2, and at both of those points in time, it is speeding up. Okay? Let's see what else awaits us here. All right. A vase is left outside in the rain. Poor vase. Poor vase. The table below gives the rate at which the vase is being filled with water. So this is a rate. You've got to pay attention to that. It's the velocity they're giving. Use the table to approximate the instantaneous rate at which the rate is changing. In other words, they want us to find the rate of change of the rate. And they want us to find that at 30. Now, remember, we are approximating an instantaneous rate, which is just a low-key way of saying do an average rate. So the average rate of change is not a derivative, it's a slope. And it's going to be a slope of the two values that have a time closest to the one that we're interested in, which is 30. Oops, just a second. I'm having trouble with my video here. Just a second. Okay, oh well. So that would be these two, 20 and 10. So at 20 and 10, we're going from 1 to 1.2, right? Subtracting those, we get 0.2 over 10, which is going to be 0.02. And you want to get your units once again, right? The top came from this column, this row here, which is inches per minute. And the bottom comes from this row up here, which is minutes. So it's inches per minute, or in other words, inches per minute squared. And it's an acceleration because the first thing they gave us is a velocity, if you will, although I don't know if those are quite fair words to use when you're talking about rain filling up a vase, but it's like the second derivative and first derivative. So there's that. Let's go ahead and do uno mas. Number 6. Okay, the graph of f of x is given above. Determine if f of x is continuous and also determine if it is differentiable at each of the x values given below. If it's not differentiable, explain why. So our first one we want to look at is x equals -7, which would be right here. Well, I see that there are no holes, there's no gaps, there's no jumps, there's no cusps. So you guys got to remember that for that would mean it's continuous basically. So for part A there, we're on number 6A. For 6A, it's going to be continuous, and our reason for that is because the limit exists. And so does the function, and they are the same thing at that point. They're both 0. So it's continuous because of that. And then we can say that it's also, well, I don't want to put B yet. We can also say that it's differentiable because not only is it continuous, but I can also tell that there's no cusps there. So since there's no cusps, that means that the slope from the left is equivalent to the slope from the right. Okay, and so it's smooth and continuous, so therefore it's differentiable. All right, next one. Let's take a look at part B, x equals -3. X equals -3 right here. Now, There's no holes, gaps, or jumps, so it's continuous. So we would say once again here, continuous, because the limit as x approaches -3 of the function is equal to f of -3. The limit is the same on the left and right, so the limit exists, and the function equals the same thing, so that's continuous. But it's not differentiable, and the reason it's not differentiable is because we have a cusp there, but that's not the reason we're going to give. The reason we're going to give for it not being differentiable is because the limit as we approach -3 for the slope is not the same thing as the limit as we approach -3 from the right. Cusps have different slopes to the left and right, so it's not differentiable. Last one, C, we want to test what's up with x equals 2. It's not continuous. Now the reason it's not continuous, it's not because the limit doesn't exist. The limit exists. The limit is 3. It's not because the function doesn't exist. The function does exist. It's right there. It's 0. The problem is those aren't the same point. So we would say not continuous since the limit as x approaches 2 is not equal to the actual function's value at that point. Okay. Now, if a function is not continuous, it cannot be differentiable. So we would say not differentiable, and our reason for that's going to be a little bit different than the last one. It's just, you could actually just use this as a reason too, because, or you could say since it's not continuous, because in order for a function to be differentiable, it has to be continuous. It doesn't have to be continuous to be differentiable, but it does have to be, I'm sorry, I think I said that wrong. It doesn't have to be differentiable for it to be continuous, but it doesn't have to be, okay, I'm going to stop talking. You guys have the idea there. All right, anywho, there's our answer for that one, and I'll bid you guys happy studying. I got to figure out how to turn off this video. Get out of the way. She is. I still haven't turned it off.
Oh, it's videotaping?
Yes, it is.
For the video.
Now, I need to figure out how to turn off this video because it's being crazy.
Did you hear us stopping?
Yes. I'm having trouble getting this thing turned off. It's really lame because it won't let me get to the freaking recording button.
It's, oh.
Stupid.